Interference is evidence of light's wave nature. So we're able to see light actually interact with itself. That's called interference. There are two types of interference. There is constructive, which is when the two waves are in phase with each other. They peak at the same point and they minimize at the same point. Together they come together and give twice the amplitude. Then there's a second called destructive interference. This decreases the amplitude. I should say that they don't have to be completely in phase with each other to be constructive or destructive. It's just the idea of whether or not the wavelengths add or subtract from each other. The result of this is called an interference pattern. We saw this before. That was when I shone the laser through those two slits. So the result of this is called an interference pattern. Interference pattern. Or identified as interference fringes. This consists of both bright and dark spots. These bright and dark spots are caused as the waves interact with each other. Classic example of this is light passing through two slits, as we talked about before. The bright fringes are numbered by integer as 1, 2, 3, with m being the maxima, and they go outward from the center. Brightest fringe is at the midpoint. The brightest fringe is at the midpoint, and it is m equals 0. So the brightest fringe is at m equals 0. This is called the central maxima. Central maximum. This idea is most clearly shown in Young's double slit experiment. So in Young's double slit experiment, he shone light through two slits, and what he observed was an interference pattern, like we saw before. He studied the interference patterns, and so the setup is light passes through the slits and it travels a distance to any point on the screen. And the slits are around 0.1 millimeter wide and separated by around 0.5 millimeter. So the slits themselves are very small and they're relatively close together. Also, we assume that L is significantly larger than D. So L is the distance from the slits to the screen that we're observing. So this is L. These are the two slits, and this is the screen, or just whatever we're seeing. But when we were doing it in class, it was the ceiling, just wherever the light is showing. We were talking about before how to get the constructive interference, so to get where these bright fringes are, so there's bright and dark spots. To get the bright spots, what we want to do is we want to have a path length between each of the slits, between the light traveling from each of the slits. The path length has to be equal to 1 full wavelength to get constructive interference. So if you imagine that light is coming out if you imagine that light is actually coming from all of these points here, the path length between this one and this one will not be a full wavelength. So we will only get it where a full wavelength, where this distance between the two path lengths is an increment of a full wavelength. So for this we say that delta R is equal to D sine theta, where D is like the hypotenuse of this triangle, the distance between the centers of the two slits, Delta R is this. Here's the path length difference. And we have theta is the angle between the two. So delta R is equal to d sine theta. Technically it's sine theta m because again it can be any integer of wavelengths. And so that becomes d sine theta m is equal to m lambda, because it can be any integer of wavelength. At small angles, at small theta m's, so at small angles, we can use the small angle approximation, which is where sine of theta is approximately theta, tan of theta is approximately theta. I will remind you that this only works in radians. So the sine of this angle in rads is approximately that angle in rads. Tan of an angle in rads is approximately that angle. In degrees, you can think of this as this is valid at about anything less than 20 degrees, which is most of what we will be observing. So for the most part, you can use the small angle approximation. If we were to sub in just theta for that sine theta, we can then get theta m is equal to m lambda over d. It's just plugging in the small angle approximation up here. This is valid for m is equal to any positive integer, and where theta is in radians. We're able to calculate the positions of the bright fringes for a double slit interaction. So each of these slits is, each of the maxima, each of the bright spots is actually the same distance apart from the others. So if we look at here, there are a lot of bright spots and they do get dimmer, but you can see that they are actually the same amount of space apart. We're able to calculate that distance using math. So we have, so if the distance is ym, so we have, this is our length. This is the distance from the slits to the screen. So slits to the screen, that is our distance L. Now we have our distance from the central maximum to whatever spot you care about. So this is ym. We also take this line, so just from the center of the two slits. Again, so we're able to just go from the center of the two because we assume that this L is so long that the distance between these two slits are essentially at the same place. So that's an assumption that we're making. L is so big that these slits might as well be at the same place. So this is our angle theta. So that's the angle theta from the central maxima to the maxima that we care about. And we're able to see that here. This is our theta, this is our ym, and our angle. So we have that ym is going to be equal to L tan theta. L tan theta m. Because this theta would be different if it was going to y1 or y2 or y3. So as long as we're talking about if we're talking about the second maxima, then this would be y2 and theta 2. As long as those subscripts match, you're good. This tan theta falls under the small angle approximation, where tan theta is approximately theta. So we're able to say that that is approximately equal to L theta m. From the previous page, we said that theta m is equal to lambda over theta m is equal to m lambda over d. So we're able to say that L, we're able to take the theta m and call it L m lambda over d, because we're still talking about the same angle as we were before. Combine all that, do some algebra, and we get an expression for ym, which is m lambda L over d. So those are the positions of the bright fringes. As I said before, these bands are equally spaced. So if you take them being equally spaced, you have essentially 1 times a constant, or like 2 times a constant minus 1 times a constant, you get 1. So these go away, and we get that the distance between the maxima is equal, so we have delta y equals lambda L over d. So that is our distance between central maxima. So that is our distance between maxima, between the areas of constructive interference, the brightest points. So that is our distance between that and that, between that and that, that and that, and so on. We're able to do the same thing for the dark fringes. So dark fringes are going to appear at areas of destructive interference. Bright fringes occur at constructive, dark fringes occur at destructive. As a result of that, since the bright spaces are at integer values, the dark spaces are going to be at those integer values plus a half. So the distance from bright to bright is 1. The distance, if this is our central maxima here, if bright to bright is 1, then bright to dark is a half, and then dark to dark is a half, but in terms of away from the central maximum, we will be looking at half integer values from that. So we have delta R, so our space between them is going to be equal to the maxima plus 1/2. So theta m is going to equal m plus 1/2 times lambda over d. So that's our theta values. That should actually be approximately. We're going to call these dark fringes y prime. So our maximas were at ym, our minimas, or our dark spaces, are at y prime m. So these are going to be equal to m plus 1/2 lambda L over d. So it is the exact same idea as what we had before, except now we're going between the light fringes. And with that, we end part 2. Part 3 coming soon.